Testing. So good morning, everyone. I'm Tammy, and welcome to HKUST in such a cool morning, with a little bit showering actually. Well, I believe that all of you here today really love mathematics and science, because otherwise you won't get up early in the morning, leave your bed, and then come to our campus under such a weather. So actually today is our first lecture of our HKUST IMO 2016 lecture speaker series, and we are very great here to have Dr. Ezra Getzler with us today here. So before the lecture, I would like to give you all a very brief introduction of what IMO is. The International Mathematical Olympiad, IMO, is the world championship mathematics competition for high school students. And you just maybe you just noticed in the video that the first IMO was held in Romania in 1959 with 7 countries and regions participating. Oops. Okay. So IMO 2016 here in Hong Kong. So next year, Hong Kong is proud to host the 57th IMO in July 2016. And the competition will be hosted by IMO Hong Kong Committee Limited, with HKUST here as the host university, and Education Bureau will be the supporting organization. So the event will be held in July for the 10 days contest and activities. So more than 1,000 of contestants and participants, they will be here in our campus and have their exciting IMO next year. And we are all looking forward to this world-class event, and I'm sure that all of you as well. So for the further updates for the IMO 2016, please stay tuned on our official event webpage and also the Facebook page. So here, may I invite Professor Wang Yang, our department head of the Department of Mathematics, UST, to give us a very brief introduction of our speaker.
Okay. Welcome. So, as a member of HKUST, we are actually very privileged to be able to host this event next year. And I also want to say that many of you, obviously, you have listened to our promotional video, and you have, Tammy also did a little bit of introduction. I think for many of you, especially I see a lot of kids who probably aspire to be a mathematician or a scientist. Okay, so you already dream. I mean, you have a dream. You want to be a mathematician, top-notch mathematician. And I can say that for many of you, IMO will be perhaps the beginning of realizing, the beginning of the journey that realizing that dream. Okay, so in fact, I want to say a few things about Ezra, and I'll mention that in conjunction with what I just said. So Ezra and I were fellow graduate students together at Harvard, and when you look at the last time Hong Kong hosted the Math Olympiad, which is in 1994, actually one of the winners, okay, realized her dream to be a top-notch mathematician. She actually became the first. Actually, I want to quiz Ezra about it. Okay, so she became the first woman to win the Fields Medal in mathematics. Okay, she was she wasn't, she weren't there when Ezra and I were there, but her advisor were our classmates. In fact, he was a fellow graduate student. If you draw a line between my office and Ezra's office, I think it was right in the middle. Wasn't that right? Yeah, you don't remember. Okay. So obviously in anticipation of the IMO, and so in anticipation, we as a university have made some commitment to promote mathematics and to attract talent into mathematics. So one of which was the lecture series, which Professor Getzler will be the first speaker for this lecture series. The other one I want to mention, okay, and I hope we have a little bit of time after the lecture to talk about it, is we have also established a elite class in mathematics called SS Chen class, which is in, I guess, in honor of one of the great mathematicians who is also a ethnic Chinese, and he was born in China. So I hope Dr. Li will have time to talk a little bit, because he will be in charge of that class after the lecture. So without further, let me just, it's my great pleasure to introduce Dr. Ezra Getzler. Ezra is, as I said, was my classmate. He was very noisy when I was a graduate student. Our office wasn't too far away, okay? So, but his voice was very loud that I had to shut my door just to concentrate on mathematics. But you were a couple of years earlier than I was, right? So, and I looked up to him because he seemed to know so much more mathematics than I did at the time. So he was, quite significantly more advanced. And so when I finally saw him again at a party in Hong Kong, and I realized he can talk. So why don't I get him to talk to you, okay? In fact, he was known to be very energetic, a good speaker, and he is very engaging. So, I don't have to, you can read his credentials here. But after the class, if you would like to have an opportunity to engage him, to talk to him, to get his philosophy, just don't ask him what kind of beer he likes. Okay, so ask him. Please feel free to do so. Okay, so now why don't we just give a good hand to Pascal.
Testing. Testing. Testing.
No, I don't think it's turned on.
Testing. Oh, excellent. Well, this is so much fun. I am told that it's midwinter here. It's okay though. In Chicago, midwinter, it might be minus 17 or 17. So it occurred to me the very first thing I'd better explain is where I'm from. Although I'm originally Australian, I teach at Northwestern University. And how many of you have heard of, none of you have heard of Northwestern University? Yeah, it's, so Northwestern University is not in the northwest of the United States. It's in Chicago, which is a country, a city which is maybe a bit actually towards the east of the United States. But when it was founded in 1853, it was in the northwest of the United States. The United States has moved west since then. So we're very proud at Northwestern University we have about 40 students who are studying for their PhDs. And 2 of them are from Hong Kong University of Science and Technology, so we're very pleased about that. And so I'm very pleased to be able to come here today and give you a talk on one of my great loves. Everything I talk about today will be up until about 1800. So it's a very classical subject, Bernoulli numbers, and but they're still used today. I use them pretty much every day in my work, which is in mathematical physics and things like that. Okay, so let's see. So thank you. Yeah. So the beginning of the subject is to think about the problem of adding all the the numbers from 1 up to, all the numbers from 1 up to n. So n is some number, maybe 3, or maybe 15, or 1,000, and let's add up all the numbers from 1 up to n, and let's see what we get. So if you do it, the general formula is you get n times n plus 1 over 2. And we can see that in action. 1 is 1. 1 plus 2 is 3. 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 plus 4 is 10. And you begin, I hope, to see there's actually a pattern. There's a formula for all of those numbers, 1, 3, 6, 10, where you take, for example, 3 times 4, that's 12, divide by 2, and you get 6. Okay? So the whole talk is going to be about those kinds of formulas. That's where the Bernoulli numbers arise. The thing is, we're going to add not just the numbers 1 up to n, 1 up to 100, but we're going to add maybe their squares. Let's see what happens if we add 1 squared plus 2 squared plus 3 squared, and so on. So, oh, I have one more triangular number, and now so there's a formula. It's amazing. So this formula goes back a long way. I actually don't know exactly whether the Greeks knew this formula, but I think this formula was probably known at least 500 years ago. And we can test this formula. It's a lot more complicated than the other formula, isn't it? The other formula, you just had to multiply 2 numbers and divide by 2. Now we have to multiply 3 numbers, and it's not clear even what the pattern is. It's hard to say. If you look at n times n plus 1 times 2n plus 1, why are we multiplying those numbers? But the point is that this formula works, and it's not too hard to prove it. So you can continue like this. Why are they called the pyramidal numbers? I wrote pyramidal numbers, but the point is, if I take tennis balls and I put down a square of 5 by 5 tennis balls, then I can put a square of 4 by 4 tennis balls on the next layer, 3 by 3, and so on, and I get a pyramid. Okay. Once we go beyond squares, it's going to be harder to imagine what these numbers look like. But that's the thing about mathematics, we can get a bit more abstract. Okay, here's some more. I've got to tell you, I don't know these numbers. I would have to sit down and calculate them. None of the formulas in this talk I can remember without my notes. Okay. So, could we find a formula for the kth powers of the sum of the kth powers of some sequence of numbers? So if k is 3 or 4, can I find a formula for the cubed powers of all the numbers from 1 up to 100? Okay, you have 30 seconds to try. So anyway, yes, you could do it. I think I've shown you a bit of a pattern already, and so you might be able to guess an answer. So this is this talk is about this question, finding a general formula. Okay? So that question was posed by this dude. He discussed the case of cubes. All right? Therefore, I guess it's clear that the pyramidal numbers he already knew. So I've answered my question. So he lived in Gerasa, which maybe if you've seen in the newspaper recently, there's a big war going on in Syria, and Gerasa is just to the south of Syria in a country called Jordan now. And at that time, it was part of the Greek world. Alexander the Great had conquered much of Asia, and there were Greeks living all through Western Asia and doing mathematics. Okay? So he was interested in a formula for the sum of the first cubes, and he discovered this remarkable formula. Okay? Which is very remarkable, I think. Let's see if we can prove it. So this is, I've lost my, hello? I'm okay? Yeah. So the proof uses something you may have seen before, mathematical induction. Have any of you heard of mathematical induction? So the idea is you check that it's true for n equals 1, and then you show that if it's true for n, then it must be true for n plus 1. All right? And so to do that, let's see, is it true for n equals 1? What's the left-hand side of this formula when n is 1? It's just 1 cubed, which is 1. What about the right-hand side? It's 1 squared, which is also 1. So it looks like it works for n equals 1. All right? It's not clear why it works, it just happens to. It's a coincidence. But that's going to be the seed from which this formula will grow. Okay? So let's see how this goes. So suppose we've already shown that this formula is true for n. So think maybe it's true for 100. Suppose we know that it's true for 100. And if you have a calculator, don't do it now, but if you have a programmable calculator, I think you should be able to show that it's true for 100, for 150. You can check it for lots and lots of big numbers. Okay? So what are we going to do? Let's see what happens to the right-hand side. The right-hand side is a square whose side is the n plus first triangular number. Okay? And I'm going to divide it into 4 rectangles. 2 of them will be squares, and 2 of them will be rectangles. So let's see a picture. So you see, there's my picture. The top left square, which I've labeled A, that's a square whose sides are the nth triangular number. And the whole thing, the large square surrounding everything, is a square whose side is the n plus first triangular number. And what I'm going to show is that on the inside of this square, we have the sum of the cubes of all the numbers from 1 up to n plus 1. So how do we show that? So, well, we already know what the top left square is. We know what its area is. It's n plus 1. Let me try again. The A is 1 plus 2 plus up to n, all squared. B is this quantity. It has one side, which is n plus 1, and another side, which is n times n plus 1 over 2. Multiplying those together, I get a rectangle with that area. I've got a pointer, don't I? There. So that's the area of this rectangle. Well, C is the same shape, but it's on its side, so we get another copy of that. And finally, D, we just get n plus 1 squared. All right? Now we have to play with that a bit. Well, we already know that's the point of mathematical induction. We already know that this equals this. That's what we assumed. And B and C add up to n times n plus 1 squared, and then we have n plus 1 squared. And guess what? If we add these together, we get n plus 1 cubed. You can do the algebra there. And that's the end of the proof. Okay? So that's pretty much what Nicomachus did in Gerasa in around 70 AD. So 950 years ago. So we've got all these different formulas now. We have a formula for the sum of the numbers. That's the triangular numbers. We've got a formula for the sum of the squares, the pyramidal numbers. We've got a formula for the sum of the cubes. That's Nicomachus' formula. Where is all this going? I don't see any pattern. And is Nicomachus' approach going to be a guide for us moving forward? The answer is no. So this is a bad joke. The proof I just gave you is a red herring. It doesn't tell us anything about the bigger picture. Okay? So we need to step back now and look at this from a more abstract, mathematical way if we're going to make any progress. All right? So the next person who contributed to this subject, his name is Johannes, and he lived in a southern city in Germany called Ulm, which is in Sweden. And that is probably a picture of him. Okay? So he was interested in the general question. We've done sum of cubes. He then moved on and began to think about sums of higher powers. Okay? And he showed that as a function, you fix k. So let's say k is 6. He showed that the sum, that this sum of, say, the 6th powers from 1 up to n is as a formula, there's a formula for it as a function of n. It's what's called a polynomial in n of degree 7, 1 higher. If any of you have any of you looked at integral calculus? I don't know where in high school you've reached. If you've ever done integral calculus, you'll see, or when you get to do integral calculus in the future, you'll see this is the beginning of calculus. Because in calculus we learn that addition, this sum here, is an approximation for something called the integral. And so this looks a lot like the integral of the kth power x to the k. And that is the k plus first power up to a constant. So here we see the beginnings of integration, although here we're approximating. Integration is about the area under a curve, and here we're approximating it by a numerical process. We're adding things together so that a programmable calculator can do it. Okay, so let's see. This is the data that we already accumulated, and you see those right-hand sides. This is a polynomial of degree 1. It involves powers of n up to the first power. This is a polynomial of degree 2. It involves the square of n and n. This is a polynomial of degree 3. It involves the cube of n. When you multiply all this out, it involves some multiple of the square of n, a multiple of n. It doesn't have any constant term, as we'll see. And finally, this is a 4th power. Okay? So let's see how this goes if we go one step further. That's the formula for the sum of the first n 4th powers of integers. Okay? What a strange formula. Do you want to test it? If we set n equals to 1, we'd better get 1. Okay? So if you add up, if you add 1/5, a half, and a third, you'll get 31/30. Okay? So this isn't really that simple, this stuff, is it? And that's why that 30th is there, that minus 30th, because we know that for n equals 1, we'd better get 1. 1 to the 4th power is actually 1. And so the right-hand side had better equal 1. So that's why that minus 30th had better be there. And that's, now we have a Bernoulli number, as we're going to see. So if we keep going like this, we're going to see these numbers. The Bernoulli numbers are the numbers that occur at the end of the polynomial. And we're going to focus on them. And if you know your Bernoulli numbers, you can give a formula for the whole polynomial. That's Faulhaber's theorem. Okay? So Faulhaber gives us a formula for the sum of the first n kth powers. So let's continue. So there's a couple of things I also want to mention. There's no constant term. There's no n to the 0 over something. There's, in other words, if the left-hand side is set to 0, the right-hand side equals 0. That is also a good thing, because if n is 0, then the sum of the first 0 kth powers had better be 0, because we're adding no numbers together. Okay, that's a very mathematical kind of geeky point of view, but ultimately that's why there's no constant term. But also note there's no quadratic term. Isn't that strange? So that's the sort of thing that studying the Bernoulli numbers lets you see. We begin to see these little patterns that we wouldn't have guessed. And so as the talk goes on, we're going to see things arise, questions about the Bernoulli numbers, and you'll see that almost anything you can suggest about the Bernoulli numbers will be wrong. If you calculate more Bernoulli numbers, you'll find out that what you thought was the case was a mistake. And you have to work harder to actually understand them. And so I'm going to now move on and talk about the big picture of the Bernoulli numbers. What do they look like in general? But I realized I couldn't talk about the Bernoulli numbers unless I tell you what the factorial of an integer is. Some of you will have seen the factorial. It has this funny notation, k exclamation mark. Okay? So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24. What is the factorial? It's the product of all the numbers from 1 up to k. Okay? Have you seen the factorial before? I'm not entirely sure when one learns the factorial in high school. Okay? What is the factorial, by the way? If I take a pack of k cards and shuffle it, I don't know, do people play cards in Hong Kong? They play video games. Yeah, I'm sorry, I can't do this with video games. Do you know what playing cards are? It's like sometimes we say, my God, that sounds like a scratched record. And then we realize that nobody knows what a record is anymore because everybody has MP3 players. So anyway, if you take a pack of cards and shuffle it, you can count how many different ways are there to shuffle a pack of cards. And the answer is given by the factorial. So they're in a playing pack, a card pack of 52 cards. If I shuffle them, there are 52 factorial different ways to shuffle a pack of 52 cards. That's that's a big number, 52 factorial. So these are the factorials, okay? And from the factorials, you can construct these other numbers, the binomial coefficients. So the binomial coefficients are also very interesting. If I have a pack of k cards, or if I own k pairs of socks, let's say, how many different ways can I choose 2 pairs of socks from my k pairs of socks? The answer is given by the binomial coefficient. So the binomial coefficient tells me that the formula can be written in this way. Oops. So if I have k pairs of socks, then I have this number of ways of choosing I of them. And it's given in a formula involving the factorials. Of course, there's a simpler formula for the binomial coefficient, but I wanted to emphasize that you can write it in terms of the factorial. So actually, maybe I should have drawn a picture of the binomial coefficients. They form something called Pascal's triangle. So, So here's the triangle you get if you write, oops, there we go. Okay, so for example, this 10 here, this is all the ways of choosing 2 pairs of socks if I own 5 pairs of socks. Okay? And so on. So this is called Pascal's triangle. So these are the numbers I sort of hoped you might have seen before. The Bernoulli numbers are a bit more exotic. Okay. So I'm going to make a table of these polynomials that Faulhaber told us to look at. So on each row, I'm going to write the coefficients of my polynomial, and we've already calculated down to k equals 4. And so now I'm going to add 2 extra rows to my table. We'll have the sum of the 5th powers and the sum of the 6th powers. And you remember, Faulhaber told us the sum of the 5th powers involves combinations of all the powers of n up to the 6th power. And the sum of the 5th powers involves all the way up to the 6th power, and the sum of the 6th power involves all the way up to the 7th power. So let's see these numbers. First, let's look at the top coefficient. Well, it looks like we understand that, right? They're just the reciprocals of the integers. This comes from calculus, by the way. So when you study integration, you'll see these coefficients. They come from integrating the powers of x. Now let's look at the next diagonal. Oh, that's interesting. The next coefficient always equals 1/2. Now let's look at the next coefficient. Okay, this is getting a bit weird. It's harder to see any pattern here. But there will be. Maybe if you are on your toes, you can find a pattern. Ah, there's a pattern. The next coefficient's always gone. It's not there. This is very hard to understand. What's really going on here? And now, we already saw this coefficient before, which surprised us. And here we see some interesting pattern. Can anybody guess what the next coefficients might be? Having asked you that, if you're able to answer it, the answer must be really easy. What would the easiest answer be? Well, 1 would be the easiest answer, but even easier than 1? 0. Oh, let's have a look. Okay, very good. So there's an interesting pattern coming. And finally, ha. Interesting. Okay? So finally, I can tell you what the subject of this talk is. It's the numbers down the left-hand column. Those are the Bernoulli numbers. Okay? So, I don't know whether... Suppose we calculated the first three Bernoulli numbers. 1, a half, a sixth. Well, we might guess then what the formula was for the Bernoulli numbers. That it was the reciprocal of a factorial. Right? Remember that the factorials were 1, 2, 6. But that conjecture is wrong because the next factorial is 24 and the next Bernoulli number is 0. So it didn't work. Okay? Well, you might say, okay, we'll skip that one and maybe the next one it'll work. But that doesn't work either. This isn't really... First of all, it's negative. And so we're not in good shape. And then by this point, we're pretty much ready to give up. And here are two more things you might wonder about from this. You might say, okay, but maybe the numerator, these are all fractions, and maybe the numerator is always 1. Well, we're going to see that's false. All right, another conjecture. Maybe the absolute value of the Bernoulli number is always less than 1. It's always quite small. We're going to find out that's also false. They're actually more like factorials in size than they are like 1. They're huge numbers. As we keep going, they're just going to get bigger and bigger and bigger without, they grow enormously. So almost everything that's true about the Bernoulli numbers, we don't know yet. It's impossible to see from this table. And that's what mathematicians are here for. To come up with, well, that's what Euler was here for. So as we'll see a bit later, Euler was the greatest mathematician of the 18th century, and he was able to show many properties which people didn't understand. So people write capital B for the Bernoulli numbers. So the K here is that K in the left column. So for example, this is B4. This is B2. Again, most of you haven't done calculus, but if you happen to have done integral calculus, you'll meet something called Simpson's formula. And if you do Simpson's formula, then there's a sixth in Simpson's formula, and it's actually that sixth. And actually, Simpson's formula refines the mean value formula for the integral, which has a half in it, and that's that half. So if you try to keep going with Simpson's formula and do more accurate versions, which is what Euler did, you get these weird numbers entering into your formulas. And actually, as you see, since the Bernoulli numbers get big, the formulas don't necessarily get better. It's, yeah, you have to be on your toes here. Okay. So, here's the formula. Uh-oh, I apologize. Haha. The formula is off the bottom. I can't because it's covered by the... I can't. It wasn't compiled, the tech. I'm sorry. It doesn't matter. The point is, what's going on is that you can see the general formula is going to involve the Bernoulli number on the top left multiplied by some easy-to-calculate fraction. Okay? So since I didn't write down the... I can't really...
Remember, right?
I don't remember it, exactly. Well, I remember the red one. So for the red one, you can see the formula is that it divides by k plus 1. Okay? The next column, it divides by k plus 1 to the 0th power. All right? The next column, so, so 1/4 is 3/2 of a sixth. 1/3 is 4/3 of a sixth. You see, 5/12 is I see what you mean. Yeah, but it's 5/4. Yeah, so so the ratios between the successive ones is always a power of k plus 1 over k. Maybe that's one way of saying it. Yeah. Anyway, there is a formula. I hope that you'll be able to download this file and you can work out the formula that fills that missing line. I'm sorry. Yeah, that's homework. Okay. Homework is that wonderful word which means I made a mistake.
Because I think the third column is very interesting. I think they will appreciate it.
Okay. Write it down. Thank you for forcing me to do it. Okay. So we want that 1/3, for example. That's the coefficient of n cubed in sigma 4n. And 5/12 is the coefficient of n to the 4th in sigma 5n. So what we have here is coefficient of n to the k minus 1 in sigma kn. And here we have the following little table. K is 2, 3, 4, 5, 6. 1/6, 1/4, 1/3, 5/12, and 1/2. So this is very hard to follow because of the reason it's hard to see what's going on is because of this 1/6 at the beginning. So let me multiply through times multiplied by a 6. And we get 1, 3/2, 2 over 1, 5 over 2, and 3. And I hope the pattern is clear. Okay? What is the pattern? It's k over 2 times 1/6. Is that correct? Yeah. Okay. So you have to try to work out what the other columns are. I'm going to move along. Sorry about that. Okay. So Bernoulli was the guy who wrote down the Bernoulli numbers. And so before I made a mistake, I said that Faulhaber found this formula. He just knew that there were coefficients. He didn't know that they were given by this explicit, beautiful pattern. So at this point, I just want to say, this is the way we do mathematics. We play with ideas. We write down lots and lots of calculations, hoping to see a pattern. And really, this is what I think all of us mathematicians do when we're doing research. We just sit there trying to find patterns by doing different little calculations or thinking hard about calculations we've done. And so that's what Bernoulli did. He knew that there was some beautiful theory, and he came up with an explicit formula for these coefficients. So he was a very, very important mathematician in the 17th century. For some reason, the Swiss city of Basel has generated lots and lots of very famous mathematicians. I'm not sure why it is. Maybe there's something in the water. These days, it might actually be something in the water because Basel is most famous as a center of the drug industry in Europe. So this guy, Jacob Bernoulli, who lived in the 17th century, so he defined the Bernoulli numbers by this formula. If this doesn't make sense to you, then don't worry about it. But you can use this formula, you can put it on a little programming calculator, and in that way you can calculate all of those Bernoulli numbers. And in fact, if I had a little more time, I could show you why these are the last coefficients in those polynomials. It's not difficult. So what's this mean? It means that if I've already calculated the first Bernoulli numbers, this formula gives me the formula for the next Bernoulli number. Because then I'll know everything in the equation except the last term. If I already know all the previous Bernoulli numbers, then of course I know what the left-hand side is. I know what k plus 1 is. I know what all the binomial coefficients are because I can read them off Pascal's triangle. And I know by assumption what the first Bernoulli numbers are. That gives me a formula for this by just subtracting all of this from k plus 1. And then k plus 1, choose k. This binomial coefficient is non-zero, so I can calculate the kth Bernoulli number. So that's what Bernoulli discovered. So you can see it works. For example, for k equals 0, it says that on the left-hand side we get 1, and on the right-hand side we get b0. So b0, the first Bernoulli number, is 1. And there it is. Okay? The next Bernoulli number is a half, and the next one is sixth. Keep those in mind. So that's how it works in practice. We have these beautiful equations, and I think you can see that if somebody shows you these equations, it's pretty easy to put it on a calculator and use this to calculate B1, B2, B3, B4. Okay? So now I'm going to finish my talk by telling you two really remarkable properties of the Bernoulli numbers. These are not obvious from anything I've told you till now. And I'm going to give you a little hint how you can prove the first property. The second property is really quite complicated. So I'll flash past some ideas of a proof, but you'll have to ask me afterwards if you want more details. Okay? So the first property is the only Bernoulli number with odd k, which is non-zero, is B1. Remember, we said that B1 is, oh yeah, thank you. B1 is a half, right? It didn't work. Oh, it did work.
Press it again.
Hover.
Yeah.
Oh, how strange. Okay, good. So, there. B1 is a half. B3 is 0. B5 is 0. B7 is 0. That's the pattern we're talking about here. So the odd Bernoulli numbers are very different from the even Bernoulli numbers. The even Bernoulli numbers we still don't know very much about. I mean, at this point in the talk. So let's see. I'll give you the one idea we need in order to prove this, but I'm not going to give you the proof because I want to have some more time to talk about more properties. So the idea is we take Faulhaber's formula and we do this incredibly clever thing. We say, what if we replace n by negative n? Okay? So you see, if we know that sigma k of 0 is 0, and we also know this formula, so this makes it very natural to extend Faulhaber's formula to negative numbers. And Faulhaber's formula works for negative numbers. That's the key point. So what we see is that at negative values of n, it's also given by a sum of powers. And if you rearrange things, you'll see there's a -1. You can pull a -1 to the k out, and we get this formula. You see, we get this formula. So if let me give an example. So we have the triangular numbers. And let me remind you, by the way, that in Pascal's triangle, it happens the triangular numbers are running down the second diagonal. 1, 2, 3, oh sorry, the second diagonal. Yeah, I've got to point at the right diagonal. 1, 3, 6, 10. Those are the triangular numbers. And so we have sigma 1 of 0 is 0, sigma 1 of 1 is 1, sigma 1 of 2 is 3, sigma 1 of 3 is 6, sigma 1 of -1 is, I've forgotten the formula, let's see, 0. Sigma 1 of -2 is, anyone? It's -1. So we get the same numbers we had on the right, they repeat on the left, but with negative values. And the reason is, the differences here are 3, 2, 1, 0, -1, and so on. You see? Okay? And I'm not going to finish the proof, but basically, a little manipulation of algebra together with this formula proves that the odd Bernoulli numbers vanish. Okay? So it's this clever trick. We give an interpretation to Faulhaber's formula in a region where we would never have guessed it would make sense, namely negative integers. So that's the first remarkable property of the Bernoulli numbers. The next remarkable property is much, much harder. So we've handled the odd ones. Now, let's think about the even ones. Let's go back and look at our column. We have 1. Well, let's forget about these two. A 6th minus a 30th, a 42nd. So I haven't given you enough data to see what's going on, perhaps, but the signs are alternating. It goes plus, minus, plus. And that pattern continues. So that's another really remarkable property of the Bernoulli numbers. And you really have to calculate and calculate and calculate. Now, Euler, I want to say, who did this, he had a very cushy job. He was hired in St. Petersburg, the capital of Russia, and they promised him there wouldn't be too many students. So he didn't have to spend a lot of time teaching. He had a lot of time for research. And he wrote more mathematics papers than anybody ever before him or after him. They fill a few shelves of a library. You might want to go and have a look in the library here at the collected works of Euler. I think it's 80 volumes. At one point, he was writing one paper a week, and he was blind. It's pretty impressive. Anyway, that's Euler. So, so there's a painting, a very famous painting of Euler. Guess where he came from? He also came from Basel. But he applied for a professorship in Basel when he was 20 years old, and he didn't get it. And so St. Petersburg, the Russian Academy of Sciences, they realized, hey, here's this fantastic mathematician, and the city he grew up in, they don't appreciate him well enough, so they quickly hired him as a professor in St. Petersburg. On a pretty good salary, And then, unfortunately, the Russian economy really went very bad. So he moved to Berlin. And then he got into a fight in Berlin, so he moved back to St. Petersburg on a much higher salary and spent the rest of his life in St. Petersburg. So Euler is the most important mathematician of the 18th century. And that's for sure. He's really extraordinary. So what he proved is that B2, B6, B10, B14, and so on, they're all positive fractions. And B4, B8, B12, B16, they're negative fractions. Okay? So it's a little difficult to complete the proof of this. I need to use trigonometry, which most of you have seen. But the trigonometry is so difficult, I have difficulty doing it. And I would need to use a little bit of calculus. And unfortunately, many of you don't know calculus. But it's not going to stop me. So I'm going to show you, so that maybe one day when you learn some calculus, you'll see that you can give Euler's proof. So the way he does it is he studies the tan function. So the tan function, I think you'll have met. The tan function, if you have a triangle, a right-angled triangle with hypotenuse 1, what am I saying? Yeah, I can't even remember what the tan function is. It's the ratio of the opposite to the horizontal. So it's the other way around. It's the ratio of sine and cosine. It's this funny function. And what we do is we take derivatives of it. So if you know what calculus is, you'll know that if you take derivatives, iterated derivatives of the tan function at 0, and they're given by this explicit formula in terms of the Bernoulli numbers. I'm not going to prove that for you, but if you gave me 15 minutes and you knew a bit about the so-called Taylor's theorem, we could prove that theorem together. It's really complicated to show, but it doesn't require terribly advanced mathematics. Okay, so let's test this. This is, actually, I should say, this is only for even k. It's false for k equals 1. So it doesn't even make sense for k equals 1. So forget it. So even k. So let's test it for k equals 2. So it says that the second derivative of the tan function at 0 is 1 times 4 times 3 times a sixth, which is 2. Okay, so let's write that down. So if you know a little, thank you. Yes. So if you know a little calculus, the second derivative is the acceleration. So it's saying the acceleration of the tan function at 0 is 2. It's this nice number. Okay? We can already make a conjecture. Maybe the derivatives of the tan function at 0 are whole numbers. Okay? And that will finish the proof. If they're positive numbers, so suppose that all of the even derivatives of the tan function are positive integers, then the right-hand side is a positive integer, but everything here, this is all positive, and there's a sign here which is alternating, and that proves that the sign of bk will alternate. So what I'm going to show you now is that the iterated derivatives of the tan function involve positive integers. Let's do another one. I'm enjoying myself. So we get minus 1 to the 4 over 2 minus 1, that's negative 1, times 4 minus 1 factorial. Anybody remember what that is? Exactly. Times 2 to the 4, which is times 2 to the 4 minus 1. 15 times B4. Does anybody remember what B4 is? Minus 1/30th. Let's quickly multiply it all out. 48. That's a positive integer. Okay. So we're in pretty good shape. So let's see how the... Now I'm really going outside high school math, but I think that's okay because we're near the end of the talk. And we say in mathematics that the end of a talk should be a bit harder to understand. So, so if I take a derivative of the tan function, it turns out that I get 1 plus the square of the tan function. That's one of the first things you should show when you learn differential calculus. So this actually characterizes the tan function. The tan function equals 0 at 0. Its first derivative at 0 is 1, and it satisfies this beautiful differential equation. And so...
Ezra, go back to the previous slide.
Yeah.
I think that should be the probably k plus 1 or k minus 1, because it's an odd function.
Oh, shoot.
Yeah.
Yes. Yeah, this is a misprint here. Yes. Correct.
Somebody is
Yes,
listening.
yes,
Okay.
yes.
So,
This should be
k
k plus 1.
Yeah.
That should be k plus 1, please. I'll correct that in the handout. I don't know how we'll distribute it. That's k plus 1. Thank you very much. Yeah. Okay. So using induction, you can prove now that all of the derivatives of the tan function are polynomials in the tan function with positive integer coefficients. So that proves the result. So that's one proof that Euler gave. So Euler, by calculating, he had a conjecture. The signs are alternating. How he came up with a proof like this, I have no idea. But Euler's second proof is much, much harder. And I can't possibly here today prove this for you because it would involve either Fourier series or complex analysis. But in any case, it's not high school math. But it involves a function that you should learn about called the zeta function. So we were summing powers of integers, and the zeta function says, what if we summed powers of every integer? What if we don't stop? Okay? So I was showing you formulas for the sums of the powers up to 4, up to 5, up to 6. And this zeta function, which was in fact first studied by Euler, but then the study of it was continued by Riemann in the 19th century. The point is, we were looking at positive powers, but now we have to look at negative powers. Because if you look at positive powers, it becomes infinite. And that would be another talk, because we know how to calculate it, even though it's infinite. It actually, we can give it a value. But that's a whole other story, also due to Euler. But let's look at the negative powers. So for example, S could be 2. And we're looking at, so now we're going to look at 1
to the minus 2, plus 2 to the minus 2, plus 3 to the minus 2, plus 4 to the minus 2, plus 5 to the, and so on. And you see, this is approximately 1 plus a quarter plus a ninth, and so on. Well, I don't know exactly how big it is, but maybe it's approximately 1.5. Now, Euler gave an explicit formula for it. It's actually equal to pi squared over 6. That's a pretty amazing formula. So pi squared is about 10. So it's actually, I was a bit off. It's 5/3, more better than 3/2. Okay? But it's less than 2. And in fact, if you make f bigger, these numbers get smaller. They're always bigger than 1, and they're always less than 2. Okay? That's the important thing to know. And this is very important in number theory. That's the main reason we're interested in the zeta function, because it can be written by factoring. This is also a misprint. This is the inverse, 1 over the zeta function. Sorry about that. Equals this. It's amazing. I've given this talk so many times before. It's filled with misprints. So 1 over the zeta function equals this product over the primes. And that already tells you something about how many primes there are. And so you can study the prime numbers using the zeta function. It turns out this formula, or the corrected one, is equivalent to the unique factorization property for the integers, that every integer can be factored uniquely into a product of primes. And that's Euler's formula for the zeta function. For positive even integers, it's given by this explicit formula. Okay? Remember I said that the left-hand side is approximately 1? So this gives us an approximate formula for the Bernoulli number. We see, finally, Euler shows us the Bernoulli number is approximately minus 1 to the k minus 1 times 2k factorial over 2 pi to the k, if k is an even integer. And so with that we see, first of all, that the signs alternate, and secondly, that the numbers, as k gets bigger, they're enormous. They're increasing almost as fast as the factorials. So nothing that we learned about the Bernoulli numbers just from tabulating them for small values tells us what they're really like. They're really these huge numbers that increase faster and faster and alternate in sign. And it was Euler who showed that. Just to finish, I'll show you some more Bernoulli numbers. So you see they get really weird really fast. If we go, we get this weird thing where 2 of them are equal, but that's certainly the last place that'll happen. Then, for the first time, we get a numerator which is 1. Then we get this completely bizarre numerator. And then, if we go one step further, we get the first Bernoulli number that's bigger than 1, which eventually had to happen because they're increasing so fast. Okay, so I have one last formula that I can't resist. This is why I'm interested in the Bernoulli numbers, because they're so important for counting the solutions of the algebraic equations. Why that is a whole other story. It's a remarkable business, but it was put into its modern form by the wonderful German mathematician Getzler, who showed this rather amazing thing. If I take a polynomial whose coefficients are the Bernoulli numbers, and I raise it to the power n plus 1, and I look at the coefficient of x to the n, the coefficient is 1. And I'll just stop. I'll finish with that. If you're willing to put a few days of work into it, you might be able to find a proof. If you can find a proof, you're ready to go in the IMO. So thank you very much.
Thanks, Ezra. This is really enlightening. I hope you get a sense of what mathematics is. It's not just the standard derivational equations, and some of you may even consider math to be boring. But I hope after you have listened to Professor Getzler's talk, you will find mathematics to be utterly interesting, intriguing, and maybe challenging. Right? So he already left a few homework for you guys. I hope you will find the proof. Now, do we have any questions? Anyone? Any questions? Feel free to. He's always looking for people with good questions. He may even promise to mentor you for the IMO if you ask a nice question. Okay?
Do you have a question? Maybe you can.
I already pointed.
You already. Yeah. That's true.
Any questions? From students, teachers, professors? Very
silence. Yes. Do you want the microphone?
Maybe not.
Okay.
Maybe we suggest you use the microphone so that around the
here is the microphone.
Hi.
Hello.
So how do you find yourself be good at mathematics, or maybe just be interested or loving mathematics?
Aha. Yeah. So I am actually a mathematical physicist. So I became interested when I was still in primary school in the elementary particles in physics. So I'm just answering for myself. Every mathematician will have a different answer. So I got interested in these elementary particles, and that meant I needed, or I wanted to learn some quantum mechanics. Because if you want to understand the elementary particles, you have to know quantum mechanics. And what I found out is if you want to know quantum mechanics, you have to know about linear algebra. And you have to know about complex numbers. And you have to know about all these different things in mathematics. And so once I started learning mathematics, I liked it more and more. And I, for example, learned Hirzebruch's theory in order to, I even wrote a book on it, in order to understand better questions in physics. So there's a very famous physicist and mathematician, Edward Witten, and he has maybe shown how advanced the mathematics that you need in physics can be. So that's one answer. But another answer might be, suppose you start using a computer to calculate. You'll find your calculations never end. And you start thinking, how can I make a computer calculate faster? Like, much faster. And then you also get into thinking about linear algebra, Bernoulli numbers, complex numbers, and how to program them to make things go faster. And actually, a lot of the mathematics you learn is the same, because there's a lot of common mathematics that gets used in many different directions.
Other questions? Something similar? Yeah. No? Any other questions? Okay. If not, let's thank Professor Getzler again. Yeah.
So in the Bernoulli numbers for diagonal, you work out, so we still not know many properties on the diagonal.
No, we know all, as soon as we know the Bernoulli numbers, I think we can say we do know the Bernoulli numbers.
I mean the matrix.
Yeah, we know all of the entries.
Once you know the Bernoulli numbers,
Yeah.
there's a formula for all the other entries.
Oh,
I left it out, I'm sorry. I can give it to you. I have to look it up. But it was in the first version of the talk, but I wanted today's talk to be a bit quicker. So I left it out. No, that's completely known, and that was what Bernoulli did. I'm sorry if I didn't make that so clear. Yeah.
Other questions? Okay, so maybe let's give Professor Getzler a second round.